Properties. Halogens are typically nonmetals and have 7 electrons in their outermost shell, with the valence shell electron of Ns2 and p5. If you observe carefully or well, you will see that these halogens have got this type of electronic configurations. They have got this type of electronic configuration of which they have Ns2 and Np5. We can see this when we scroll up and reach on the electronic configuration of chlorine. You can see it's 1s2, 2s2, 2p6, 3s2, 3p5. So we can see the highest energy level is 3, and the orbital is s and p, and they have all the valences, they have all the indexes of 2 and 5. So this is the general electronic configurations of chlorine, of chlorine and all groups 17 elements in common. So as we continue in the properties, we've seen that the elements in group 17 exist as diatomic molecules. You observed it as fluorine, chlorine, and bromine and iodine. Even though all of them, they are not the same, but all of them exist in diatomic molecules, which means that they exist in a combined state. You can never ever find one in a single state. They all have molecules, they don't have monoatomic structures. So we have also physical states. So when you go in physical states of chlorine, here we observe, or of group 17 elements, here we observe how are they surely how, like for example, chlorine is gas. It has this type of color. Like we're going deep on how they appear or the physiological part of these elements. So as we dive in deep, we see that fluorine and chlorine exist in a gaseous state because of bromine, because of bromine is a brown volatile liquid and iodine is a solid, all at room temperature. So here they told us the reason: as the sizes of halogens increase, the van der Waals forces increase, which means that since fluorine and chlorine are small and they are held by fewer van der Waals forces, so these van der Waals forces are forces that hold electrons that holds can say like atoms together. So you observe like in graphite there are some forces that hold two layers together. So these van der Waals forces, let us see what. So van der Waals forces, Waal forces. So as you know, these van der Waals forces are just weak forces that exist in between two molecules, or which are combined in any state. So as we continue, we see the melting points of these elements. So these elements, they have different melting points. So we can see that fluorine, it is the one which has the least melting point, which means that this one has a high volatility, which means that it is more volatile than other gases. So when you go on chlorine, we can see that chlorine also has, it's the one which is following fluorine in the melting point. So as we see, it has negative 101, and fluorine has 219. So this means that chlorine and fluorine they have critically low melting points. So same to their boiling points, as you can see, negative 188 and negative 34. They are not high numbers or high values that we can assign to these elements. So these elements, compared to other elements in the same group, they are in gaseous state, which means that they evaporate from a lower temperature. So as we arrive on bromine and iodine, the characteristics change. So we can see that bromine is a liquid and iodine is just a solid. But when you see iodine, also iodine, when you apply too much heat, it also has some way, some how it just sublimates it. I've never seen iodine in a liquid state. So for it just sublimates. So here they say that the boiling point on and the melting point of halogens are low because they are held together by weak van der Waals forces of attractions which are easy to break. So I told you van der Waals forces. So van der Waals forces are types of weak intermolecular force that play a crucial role in properties of molecules and materials. They are named after a physicist Dutch Jan Diederik van der Waals. So these forces can be London dispersion forces. They can be Debye forces. They can be Kisan forces. So these are different types of van der Waals forces. So van der Waals forces, they are weak intermolecular forces. They means if fluorine, we've seen that they exist in a diatomic structure on they exist as diatomic molecules. So this means that in their molecular form they have strong or weak van der Waals forces. So chlorine and fluorine, they have weak van der Waals forces, which causes them to have a low melting point and a boiling point. So you understand, if one magnet, let's take a reference on magnets. So if we have magnets which are not like weak magnets, the weak magnets will not attract as high as magnets which have high power. So compare it in that way. So separating them, it's easy. So when we apply heat also, it separates it weakens the van der Waals forces, causing these cases to evaporate. But particularly on fluorine and chlorine, we've observed that they have a low boiling point due to these weak van der Waals forces, or in simple words, intermolecular forces. So let's continue and see. So there are also different trends that exist in these group 17 elements. So we've seen that they have also boiling points. So the boiling point and melting point decreases down the group. So as you understand, as the van der Waals as it increases, so as you understand, as the van der Waals forces increase, so the melting point will increase, the boiling point will increase, because the heat energy that will be required, or the temperature that will be required to separate those strong van der Waals forces will be much more than the energy which will be required to break down the van der Waals forces, like the ones which are present in fluorine and chlorine. So as we continue, we see that as the sizes of hydrogen increase in magnitude of van der Waals forces, the forces that I was saying, the temperature required to break the forces also increase, hence the increase in the boiling points and the melting points. So this is how it happens. So when you go on bond energies, so it is the energy required to break down a single covalent bond. So here we have different elements and their bond energy. So I can say like this bond energy, it's like it's like ionization energy, or how can I describe this? So bond energies, this is the energy which is required to break. Like you see, if chlorine occurs in a diatomic form, so we have a way that we can break it using some heat. So this energy is the energy needed to break fluorine from its combined state to a monoatomic state. So here is the trend between these energies. So the bond energy decreases down from group from chlorine to iodine. So as the size of atoms increases, the bonds between the atoms also weakens and decrease in the energy required to break the bonds. So as you know, the as you know so how am I gonna explain this? So as you know, as the atomic radius increases, this is the distance from the nucleus to the outermost shell. So as it increases, so this weakens the force of attraction between the nucleus and the last energy level or the shell. So this thing causes like a decrease in the force of attractions, which decreases the bond energies. So as you know, the rest shell of an atom is the one that reacts. So this one causes a development of forces. Or no, it's not forces. It's like this develops something like weakness between two bonding elements. Hence the energy needed is reduced. So as you see, if something is weak, the energy which is needed to break it is just less. So here is why fluorine is not compared with all these ones. So the abnormal low bound energy of fluorine is because fluorine is a molecule. Fluorine molecule is very small, causing strong repulsion forces, strong repulsion between lone pairs of electrons and on fluorine atoms. So as you understand, fluorine is very small, and these lone pairs, these bonded electrons, these which are bonded to oneself, are the ones which they have a strong repulsion to the electrons, which are they have like a strong repulsion. So if I say about strong repulsion, understand like it's a magnet which is repulsing another. So these fluorine lone pairs, so for them they are already bonded. So we have like something like a fight on uh, on the outermost energy level. Hence these are lone pairs, because they are like if I count well, these are four lone pairs. Yeah, these are three one round pairs which are just repelling to each other, hence reducing the force of attractions between these molecules. So that's why fluorine is not compared within these elements.